Yeah, good evening, students. Today we may have some noises because I'm in office, and it seems there are some renovation work is ongoing. Okay, almost 7 p.m. Can you all hear me? Okay, great. Yeah, because there are some noises outside my office. So if you cannot hear me clearly, please let me know. Okay, yeah. So I look at the GBA groups. There are 4 students who have not joining a GBA group. Let me share the screen. So if you are one of the member, you have no choice now. You can see these are the 4 students left without a GBA group. Okay, so after today's seminar, I will drag all the 4 students into GBA group 6. Okay, yeah, so you need to work on with each other closely, work on the GBA assignment. So actually after today's seminar, you should be able to do I think at least the question 1 from A to C, right? Yeah. And some maybe you can maybe 1D also, because we will discuss the simple or moving average and exponential smoothing. Okay, yeah. So after today's seminar, I believe you should be able to work on the GBA assignment. Okay, yeah. All right, so let's start with today's lesson, because today we also have a lot of things to cover, right? Compared to what we discussed in seminar 2, a lot of things to cover. Okay, so before we discuss question seminar 3, so let me quickly go through what we learned in seminar 2. Okay, so in seminar 2, so we need to first look at your data, right? Raw data. And then once you convert the raw data and input the data into R, you need to look at whether there are outliers or missing values, right? So for outliers, we can use the interquartile range to determine whether data is an outlier or not. Okay, you can actually use the box plot to see whether some data are maybe abnormal or is maybe strange. Okay. However, unless you are very sure, okay, you should contain or maintain all the data. You should not remove any data or change the outliers. Okay. And for the missing values, okay, for the missing values in time series, so either you can replace the missing value, fill the missing value with the series mean if the series is stable or stationary, right? Or have no clear trend, no seasonality, no cycles, okay? If otherwise, you may need to fill up the missing value, replace the missing values with interpolation method, okay? And so you can use that function, right? You can use a proxy function to replace the missing value with the interpolation method. Okay. We also discussed the backshifting, foreshifting, right? And we discussed we use the TS explore function in R, right? In the TS forecast package to before you do any analysis, you can see the trend, the seasonality, the cycles, the variability of your data. Okay. And so the TS explore function is very useful. We also employ this function in today's seminar. Okay. And we also learn the correlation, autocorrelation, partial autocorrelation. Okay, and actually these are very important statistics that will be used in seminar 4 and seminar 5, which help us to determine the model. Okay, the order of the model, for example, ARP model, MAQ model, or ARMA-PQ, ARIMA models. Okay. We also discussed the decomposition of a time series. Basically, there are four components in a time series, right? So we have a trend. Trend, it is depending on the time, whether it is increasing or decreasing, right? And upward or downward, okay? And we have cycles. So cycles, we also have seasonality, right? Seasonality, we also have random irregularity, maybe random factors, random disturbance. Okay, we use a TS decompose function to decompose a time series into different components. Okay. All right. So let's look at learn the smoothing a time series in today's seminar. Okay. So because now we are dealing with a non-stationary time series, okay? And so there could be trend, there could be cycles, there could be seasonality, okay? So let's first look at how we can use various methods to smooth a time series, okay? And yeah, if you look at the time series, if there is a clear trend, right, you need to consider how to so-called fit the trend, right? So we usually use this regression, right? Regression to capture the linear trend, or sometimes a bit non-linear trend, depending on what the terms in your regression models. Okay, so regression is the method we can use to fit the data. If you look at there are some maybe patterns of your data. And for regressions, I believe all of us learn this in your undergraduate programs, right? So we use the least square method to estimate the parameters in regression models, right? So this linear least square method actually minimizes the sum of the squares of errors. Right? When you fit a model and you have the error and then you square the error, you add up all the errors for each observation, and then the least square will give us this so-called the best linear unbiased estimate, right? Sometimes we say blue, right? Blue estimate, okay? Okay, so in a time series, because you want to use the regression models to fit the data to capture the trend in your data, right? So either it's a linear trend or maybe a nonlinear trend, okay? So you fit the time series, and your dependent variable is your observation y, and your independent variable could be the time period t, or even t square or t cubic, right? Different depending on what kind of trend you can observe, okay, in your data. And there could be also seasonalities in your data, right? So you use dummy variables S1 to SL. For example, there are L seasons in your data, right? So you use these dummy variables to in your model, okay, in your regression model. So for example, if only linear trend involved, you simply model your this linear regression in this way, right? This is your observation, this is your time t, and then there is a random factor, okay? And you need to estimate beta 0 and beta 1 using the least square method, okay? And so this beta 1 actually describes the trend in the data. So now if you observe there is a linear trend, right? A linear trend in your data. So you use this simple linear regression, right, to model this trend. And so this uh, epsilon t is a random error in your linear regression model. So we, in order to ensure your estimate is unbiased and the best, right? So we need to ensure that epsilon t follows so-called identically independently distributed uh, as a normal distribution with mean zero and some variance, constant variance. Okay. And if your data have maybe a nonlinear trend, you might consider, for example, the trend may be uh, approximate to, for example, t square or even t cubic, right? You can use higher order polynomials in terms of t, right, in as an independent variable in your linear regression model. Okay. Uh, okay, so if you model your data in this way, that means there are not linear trend in your data, and there could be k plus one parameters to be estimated, right? The more terms you introduced in your model, then the more parameters you need to estimate. Okay. Okay, seasonality, right? Seasonality means there may be similar patterns across the same period within maybe within a year, within a quarter, within a month, within a week, right? The same pattern. So there are seasonal uh, effect, right, in your data. So, for example, if there are L or seasonal uh, seasons in a cycle, right? Here, in order to avoid this multi-collinearity problem, so we introduce dummy variables, and here uh, you will use L minus one dummy variables. Okay, L refers to the number of seasons in your data. Here you can see we have maybe a first season, second season, but here you can see we have only L minus one season dummy variable in your regression model. Here we model if the data have no trend, only have maybe seasonal patterns, right? You just use the seasonal indicators or dummy variable, right, to model all your data. Okay. So here we have, if you have L season, for example, if your data is monthly, so there are monthly data. So we will think that there are 12 seasons in your data. If your data is weekly data, you may consider there are maybe 4 seasons because usually a month have 4 weeks. Okay, if your data is quarterly data, and you may consider also, right, 4 seasons. Okay, and so this is the number of seasons, and then here these are dummy variables either 0 or 1. If that period in a particular season, so that variable will be 1 and all the other seasonal indicators will be 0. Okay, and however, here you can see because you have L seasons, in order to avoid this multi-collinearity problem, and we need to exclude one dummy variables, right? And for example, let's look at a simple example. For example, gender. Gender we have male and female, right? Two uh, uh, values, but you will use maybe one dummy variable, right, to indicate. For example, this gender equals 1 means it's a male. If gender equals 0, then it is a female, right? So we use L minus 1 dummy variables, right, to indicate the seasons in your linear regression, simple linear regression model. All right, so this is a seasonality in the regression, and if your data have both a linear trend, right, linear trend, and also seasonalities, so this will be the regression model you need to estimate, right, L seasons, okay, and then you use L minus one seasonal indicators in your regression model. And if you have maybe other trend, right, in terms of higher orders of time, for example, you have t square and up to t to the power of k, and then you can also estimate this linear regression model. Okay, now you need to have additional term, this t square, right? Okay, sometimes, okay, we only add linear trend will be good enough. Or maybe sometimes you consider quadratic, right? Because the model becomes complicated, right? If you introduce more terms in your linear regression model. And if you have multiplicative time series, remember, refer to what we discussed in seminar 2, the four components that could be additive pattern or multiplicative pattern, right? If you see the seasonal and maybe the trend are in a multiplicative pattern, right? So you need to consider the joint terms of the trend and the seasonal. For example, here you can see we first model this additive of each component, for example, the trend and the seasonal. Now we need to model this joint impact of this trend and seasonal, okay, joint. So this will make your model even more complicated. Sometimes may not be easy to estimate all the parameters, okay, because you introduce too many terms and many parameters you need to estimate, okay. Okay, for the time series, we will use this TSLM linear model, okay, time series linear model function to in this package to fit the time series regression model. So now remember, we are dealing with non-stationary time series. There could be a trend, there could be seasonal patterns, there could be maybe the joint impact of trend and seasonal, okay, the multiplicative impact of trend and seasonal. Okay, so we will use this TS linear model, TSLM function, right, to model this. This is what we will do. Okay, so this is the data, and the trend dot order refers to your linear, the terms regarding time. Okay, this is from include up to t cubic, right? T to the power of 3. Okay, this is a trend order. And a seasonal, okay, seasonal refers to true or false, whether your data has a seasonality effect or not, okay. And a period refers to the number of seasons in a cycle in your data, okay. So usually, for example, this monthly data, and we will consider the number of seasons will be 12, right? And then type refers to whether it is additive or multiplicative in the time series in terms of the trend and the seasonal, okay. Okay, so this is use the R function TSM in this way, and then you will get, for example, SP500 linear model, and we can fit this model. Later we will demonstrate the code. Okay. All right. So there are a few output from the model estimate. Here you can see there are intercept. Okay, intercept. So remember your model is yt equals to a constant which is for example we use delta 0, right? This constant, okay, delta 0. This is the intercept plus your trend order. For example, this is a beta 1 t, and then this is trend order 1, and then trend order 2 means beta 2 t square, okay, plus beta 2 t square, okay. And trend order 3 beta 3 t cubic, and so on and so forth. So I will not write it here. Okay, and the season, okay, season, you can see here we have a period equal 12 means we have 12 seasons, right, in a cycle. And however, we will use L minus 1 timing variables. That means you will see maybe season 2 up to season 12. There are no season 1 because you will remove one timing variable, right, to indicate to in your season indicators. Okay, so we will have 11 timing variables from season 2 to season 12. Okay, and then you have multiplicative terms. Later we will maybe now we can demonstrate this SP500. Okay, SP500. Okay, so I'm going to use Jupyter notebook. Okay, here I say this will be seminar 3 demo. Okay, so we will input the SP500 weekly data. Okay, and if ensure that you use the TS forecast package. Okay, TS forecast package uh, and SP500. SP500. Uh, we need to import the data into R. SP500 weekly, right? Weekly. So CSV. Okay, let's look at the data. Okay, so this data frame. Now you can see there are two columns. The first column is date, but it is in a character format. So we need to change this into a date format in R. And the close is the time series. Okay. And okay, so remember, when you are dealing with the time series, you need to convert the date into the date format. Use as dot date. Okay. And format. Okay. Format equals now we have a day. Right. This will be day, and we have months. We have year. Okay. Okay, so let's see whether we have changed the uh, date column into the date format. Okay, that's good. Okay, so we have changed the date column into the date format. And remember in seminar 2, there are a few missing values in SP 500 is column, closed column. So let's look at what we have. Okay, so we check whether there are so which row have a missing value. Okay, so there are you can see, remember there are six. Okay, six six rows have missing value, and we want to uh, fill up the missing value with interpolation method. Okay, so this is the because there is if you look at the close column, there is a clear trend, right? So we will use the interpolation method. Okay, so we will SP500 so ensure there are no missing values. Okay, we use the a proxy function. Okay, x equals to SP500 this date. Okay, and okay, y equals to your column which have missing values. Okay, and x out equals, so the values will be field with based on the date. Okay. Okay. And then we replace all the white column, which is the clues in SP500. Okay. Yeah. So this is where fill up the missing value. Okay. You need to have this step. Otherwise, the result, you might not be able to generate some of the result because there are missing values in your data. And then you may not be able to do the analysis. Okay. Okay, so the next step is we need to convert, right? Convert the data into a time series object in R. Okay, we use TS convert function. Okay, so this is the X is your time series, and T is the date. Okay. And you, of course, you can give a name of your time series. So we say x dot name equals SP500. Okay. All right. So this is what you need to do in terms of data preparation. Okay. So of course, you can see whether there are missing values. That should have no missing values. Or let's look at a print, maybe print SP500 to see. Okay. All right, so you can see this is the SP500 is actually a weekly data, right? Each year there are around 52 weeks, right? Up to from 2000 up to 2020, 2022, right? 2022, okay. Okay, so this is your data, and now we will use uh, time series linear model TSLM function to estimate the regression model, okay, for your data, okay. Okay. Or you want to see, for example, before you feed any model, right? You want to see your raw data and whether there are certain patterns or trend. Okay, you can use TX Explore. This is what we learned in seminar 2, right? Okay, and then trend. Let's look at the trend. Maybe equals to linear. You see the shoe dot plot equals false. Okay. And then maybe you want to see some the partial or the auto correlation ACF or partial ACF, PSF for certain legs. Maybe leg max equals to let's say 7. Okay, we use 7 in seminar 2 or 10 something, even 20, as long as you have enough data. Okay, so you can see there are some statistics you want to see. For example, some statistics, right? Covariate. We actually explored the SP500 in seminar 2. Okay, so ACF, PSF, right? And you of course you can plot. Okay, plot. You can ensure this maybe let's make it is true. Make it true. Okay. There are a few plots you can see. So this is your data after filling up the missing values. Okay, there are trend, there are cycles, there are of course seasonality. We cannot observe clearly because it is we have too much data, right? And there are irregularity, okay? And some of the, you can see the distribution of the data, and some maybe you have outliers, And this clearly the data is not maybe normally distributed, right? And the ACF, right? If you look at the ACF, you can see even after with 7 legs, and the ACF are clearly not zero, right? They are significantly different from zero. That means the time series have strong autocorrelation, okay? And okay, autocorrelation, yeah. And this PACF, okay, PACF. So after leg 1, the uh, PACF maybe is close to zero, okay, because they are within 2 standard deviation, okay. All right, so this is the you explore the data. Now let's fit this linear trend. Okay, this is regression. SP500 LMM. Maybe we use TSLM, and the data, right? The data will be SP500 close, and the trend, the order means you want to fit up to t cubic in your regression model, okay? Seasonal, okay? Seasonal equals true because there are clearly seasonal impact, okay? Effect. Period, okay? So let's say there are 12 seasonal, okay? And a type equals multiplicative, okay? So because you look at the raw data and you will see the variability seems becomes bigger, right? Uh, the variability becomes bigger when the time with the time. So we see a multiplicative model for this linear trend and seasonality impact. Okay. Okay. So let's look at this 500. We use a summary function to see so what are the output from this model. Okay. You can use print, but sometimes print could be quite messy. So let's look at this uh, model, okay, linear model. Here you can see we have in terms of the time, there are up to order 3, right? T square and t cubic. And if you look at this column, probability or p-value, right? This is p-value. P-value, the the intercept is significant, and the trend odd 3 is significant, but trend odd 1 and odd 2 means t and t square, the coefficient is not significant. Okay, and if you look at all the seasonal indicators here from season 2 to season 12, what you can see is all the p-values are very big, right? So they are not significant at all. Okay, and the multiplicative term or interaction terms, for example, order 1 and season with 11 seasonal indicators, they are also not significant, right? Because the p-value is very big, right? Bigger than 0.05. Sometimes we use 0.05, this is alpha, right? Significant level. So it is much bigger than 0.05. So they are not significant. And if we look at the other interaction terms, they are not significant at all, right? Now, if you look at the analysis of variance, okay, here trend, you can see the p-value is almost zero, means there are clear trend in your data, right? The trend should be retained in your model. But seasonality, you can see, and the trend and the joint impact or the interaction terms of trend and seasonality, they are not impact significant at all. Okay, so you might consider fitting this your model. For example, remove all the seasonality impact and remove all the joint impact, or it's not no multiplication. The type is not a no, not multiplicative. It's just the seasonal, just the trend. Okay. So this is what we can observe from the linear model, right? Using the TSLM function. All right. So can you all follow me? Do you have the same result as I'm showing here? Okay, great. Yeah, I see. Yeah, many of you should be. Yeah, we are on the same page. Okay, so let me go back to the slide. All right. So this is what we will see right here. You can see. Yeah, this is the estimate. Basically, those coefficient in your linear model. Okay. And the p-value, right? Look at the p-value, right? And almost all seasonal, right? All seasonal indicators are not significant, and the joint impact are not significant. Only the trend, the intercept, and also the trend or tree are significant. Okay. Okay. Yeah. So this is what we will have. Yeah. Yeah, you can see here the period, right? We say equals to 12. So we assume there are 12 seasons in the data. Okay. Okay, so let's do a simple activity, and we use this. We create a linear regression model for total series in the arrivals data set. Okay, and then we fit the model with a linear trend. Okay, only linear trend, and that means trend the order will be one, right? Only one. Okay, and the seasonality, 12 seasons for monthly time series. Okay, so and then we assume the series is multiplicative. Okay, and so let's do it, and I give you maybe 2 or 3 minutes. Okay, then I will demonstrate the steps. So first you need to import the data, the arrivals data set into R, and also you need to you look at the column names, and you might consider, you might need to change the total, the second or third column into total, and then make the date column as a date format, right? And then convert it to the time series object in R, and check whether there are missing values in your time series. Okay. Okay, maybe we can do it together. Okay, so let's first import data into R. Arrivals read.csv is arrivals.csv data. Okay, and you look at your data, the columns. Okay, here you can see there are a few columns. The first column is date, but it's not in date format, so character format. So you need to change that into date format in R. And then the total arrivals, so we will change the name to total, okay, to make it simple. So column names, arrivals, and the second column name equal to total, okay. And then we change the first column into date format, okay. So arrivals date, okay. And the format, you look at the format will be day, months, and year, okay. Okay, so let's look at the data. Okay, so here the first column has been changed to date format, and the second column has been renamed to total. All right. Okay, so now let's uh, convert the total into a time series object. Okay, let's convert this to a time series object. Total equals convert arrivals total, and yeah, you can say x equal to, or you can remove x. Okay, t equals arrivals date. Okay, yeah. So we convert this into a time series object, and you want to see whether there are missing values in this time series. Okay, so let's look at maybe whether there are any arrivals. And if there are no output, means there are no missing values, right? Yes, okay, no missing values. I think we checked that there are no missing values in arrivals total column, right? Okay, so let's fit a linear regression model with linear trend with all the only linear trend, and with seasonal impact, and also the trend and the seasonal are in multiplicative form, right? So this is what we required. Okay, so let's uh, fit this, maybe arrival total lm TSLM, and then data arrivals total, and trend the order equals 1. So there are only linear trend, right? And seasonal equals true. So there are seasonal patterns, and type equals multiplicative. All right. Yeah. So this is the model we fit. And then you can use summary to see the fitted model. Okay, summary arrive total.lm. Okay, all right. So this is what we will have. You can see there are uh, by default there are 12 seasons. Right, this is only a linear trend, and clearly it is significant. And you can see, yeah. So there are the intercept is also significant. However, if you look at the seasonal indicators, no significant, right? The coefficient are all insignificant, and the multiplicative terms are not significant. Maybe last one, you can see all the trend order and season 12, but it is also bigger than 0.05. so we say it is not significant. Okay. Yeah, if you look at the analysis of variance, later we will discuss. There is a table to show the ANOVA table, right, for time series. Here, trend is clearly significant in this data set. And seasonality is not significant because the p-value is almost 0.1. And trend seasonality is not significant, right? And these error measures we will learn maybe in later, okay? Training on the training data set, okay? The R square, we have R square and adjusted R square. So you learn linear regression before you know what is R square, right? R square basically measures so how much variance in a dependent variable can be explained by your model. Okay, the higher the better, right? Okay, the R square must be in 0 and 1, right? It's positive but uh, smaller than 1. Okay. So this p-value for the F statistic basically to measure whether the whole linear regression model is significant or not, right? The p-value is, you can see, is almost 0, means this model is useful. And or you can say there are no coefficients are not all coefficients are insignificant. It means there are some coefficients are significant. Okay, so the model is useful. Okay. Okay, so this is what we will do for activity 1, right? Okay, let me go back. Yeah. So activity 1. So you can see we fit this linear regression model. Okay. So what is the implication if the p-value are not significant for seasonality and trend order? Okay, that means there are no clear indications of seasonality and the joint impact of trend and seasonality in your model. So sometimes you may remodel and without considering seasonal impact of your model. Okay, so this is what we will get. For example, in this, let me go back. Okay, here, if you look at your model here, trend order 1 is sufficient, right? And a seasonal will be you will indicate it is a false, right? And then no seasonal impact. So just a linear, simple linear regression model. So let's do it. Okay, maybe so your data will be SP500. Oh, not SP500. This is rivals and total, right? And the trend, the order equals 1 will be enough. Okay, trend, the order equals 1. Seasonal. Okay, so this will be okay. So let's look at summary. This is you will refit your model because there are no seasonal patterns in your data, and so only linear trend. Okay, so you can see it's a very all the you if you look at the coefficient, the intercept is significant, and the coefficient of the trend is also significant. And then the p-value means you can see the trend, the p-value is 0, means very significant, right? And the model is also significant. Okay, yeah, this is what we mean. So if you see some of the terms are not significant, you might remove that. For example, here you have no or seasonal impact in your model, in your data. Okay, so you may not consider include the seasonal terms, the dummy variables in your linear regression model. Yeah. Okay, great. Yeah. So let's go back. Okay. Okay. So let's see. Yeah. Now regression model here. This is in your basic statistic. You say this is a global test, right? Global test means you test whether this linear regression model is significant or not as a whole, right? Okay, so so the null hypothesis, the alternative hypothesis, at least one of the coefficient is not zero, right? So you say H0 is not true or H0 is not true, okay? So the null hypothesis indicates that the trend and the seasonal components do not exist in the data. So the fit model, and because all the parameters are zero and the null hypothesis, that means your model is not meaningful, right? It's meaningless, okay? So and if the F test is smaller than some significant level alpha, for example, usually we select alpha equal to 0.05. Okay. In some cases, if you have a very large data set, maybe alpha you can use 0.01. Okay, so you will reject that if reject null hypothesis if alpha is smaller than 0.01. Okay, but usually we use alpha equal to 0.05. Okay, and if the data size is not so large. Okay, R square, right? So it is a coefficient of determination, the name, right? So the higher R square, the better your model, because the R square measures what is the percentage of variation in your dependent variable that can be explained by your model, right? And then sometimes we look at the adjusted R square. Adjusted R square means because the more terms you include in your model, definitely the higher R square. However, the more terms in your model, right, this will create a more complicated model and also make your estimate maybe less efficient. So we use adjusted R square to penalize the number of terms in your model, right? You introduce more terms and the adjusted R square may decrease, right? So this is the way you look at R square and adjusted R square. Yeah, this is an ANOVA table. This is similar to the simple linear regression model, right? We have a few components. For example, we look at the trend, we look at the seasonality, we look at the trend and the seasonality, the joint terms, and the error and the total error. And then we look at, we divide by the degree of freedom, right? For example, MSRT and the trend, if you have order of K, so there are K trend, right? And then we get this mean square error of trend. And then, for example, seasonality, right? And we look at this total error term, right? Error term, and the degree of freedom is total number of data minus the number of seasons minus maybe you have K seasons and then plus 2, right? And then we get this MSE of error. And then we calculate the F statistics. And then look at the p-value of the F statistics and to see whether the trend effect is significant or not. And we look at the F statistics of Fs to see whether seasonality impact is significant or not. And we look at the joint terms, right? So this is actually mimic the ANOVA table for linear regression model. Okay, so you don't need to remember this. Honestly, I cannot remember this. Okay, but you need to understand. Okay, you need to understand. Yeah, when we test, we look at the test of the model. We look at whether there are significant trend, whether the seasonality impact is significant or not, whether there are joint impact which is significant or not. Okay, so this will be sufficient. Okay. Yeah, so I will not go through this part. Now, if you look at your output from your linear model, right? The fitted linear model, and you look at the p-value, right? P-value of the trend. Here, look at this. It is p-value is almost zero, means the trend effect is very significant. But the seasonality and the joint impact of trend and seasonality, they are insignificant, right? So you look at this, the p-value, okay? And here the multiple R squared, right? This R squared. And sometimes you also look at the adjusted R squared. Here you can see the adjusted R squared is always smaller than the R squared, because the adjusted R squared will penalize the number of terms in your model, right? The more terms, the lower are adjusted R squared. Okay, and sometimes I'm also mentioning, right? You look at the F statistic for the whole model, okay, and then this p-value is almost zero, means the model is significant. Okay, yeah. Okay, yeah, so this is the output, and you can interpret from to make adjustment, make a judgment about whether your model is useful or not. Okay. Okay, so let's move on for forecasting with regression. So now, how to do forecasting? Once we fit the model with a regression model, so how can we perform forecasting, right? So the forecasting, actually, we try to find the most expected value, right, in future period. And so you need to have a perspective for a period, right? The T star, okay? And then for any future period, T star plus H, and then you need to you need to forecast. Okay. So for example, here you fitted this model with alpha 0 hat plus beta 1 hat, this linear trend and quadratic trend, and maybe t to the power of k and trend. Okay. And also you fit the seasonality. There are L seasons in a cycle in your data. And then there are joint impact, right? Joint impact, both the seasonal and the trend, okay, the multiplicative terms. And let's say there is a linear trend. Order equals 1 means we don't have this term, right? We don't have all the other terms. We only have the linear trend, okay? And the joint multiplicative terms of the linear trend and the seasons, okay? And suppose your data ends at t equal to 48. That means from t equal 1 to t equal 48, you have 48 data points, and you build this linear model, right, with a linear trend and seasonal impact. Okay, now you want to forecast t equals to 52. Okay, t equal to 52 also means this will be a 4 period ahead, right? And maybe this t equal to belongs to season R. Remember, there are maybe L seasons, and because t equal to 52 belongs to season R, so only S this TR equal to 1, right? As 52R equal to 1. All the other seasons, the dummy variable will be equal to 0. And remember, we have L minus 1 dummy variables to indicate the seasons, okay? All the other equal to 1. So now you estimate, you plug in T equal to 52, right? Alpha 0 hat plus beta 1 hat times 52. This refer to 52. And then the season, right? And T equal to season 2 in season R. This in season R, and this is the coefficient for season R, the dummy variable. And this dummy variable equal to 1. Okay? And then the multiplicative term of T times season S52R. Okay? And because S52R equal to 1, so you plug in into this function, and you will get the estimate for T equal to 52. Okay? So this is what do we mean by forecasting once you have fitted a linear regression model for your data. Okay. Okay, so we of course we can use the T as in R. We can use this T as forecast function, right? To do the forecast. Here is the T as forecast function. So this is a model you just fitted as P500 LM, and you want to forecast the next 12 period. N dot ahead equals 12, and you want to plot. Okay, you want to plot this. Plot only the forecasted data, forecasted values. Okay, and with the confidence interval. Okay, so this will be the output from this TS forecast function. Okay. So let's look at this. So the first parameter is the model you just fitted, right? The model object. Your forecast will be conducted because you fitted this model. And n dot forecast refers to the number of forecasting period. And forecast include this control whether the forecast values are plotted along or together with the original series. Original means when you fit the model, we fit this SP500.m LM model, right? You also use the training data, right? To you have the uh, so-called estimated data, and you have actual data, and then you want whether you want to plot all or just plot the forecasted data. Okay, and the options can be all, predict. Predict means only the training data. The forecast data means you want to forecast. Okay, so do we have? Okay, so let's demonstrate this in R. Okay, remember we have fitted this LM SP500 LM. Okay, suppose we keep this model. Okay, so we will not remove any seasons or the multiplicative terms. Okay, so we use this model because you look at the p-value. Okay, this model is significant, and this model is also very useful. Okay, so let's forecast. Okay, for the next 12 period. Okay, so we let's look at maybe just simply TS forecast. Okay, and your model is SP500, right? SP500.lm. And number ahead 12, and forecast include equals forecast. Okay, we only plot the forecast. Okay, forecasted data. Okay, so let's look at. Okay, so this is the output. You can see we forecast the next 12 period, right? In 2023. Okay, in 2023, and this is the forecast value. and the standard error, the confidence interval. Okay, so this is the plot, and because you just plot the forecasted data. Okay, so this is where we can show, right? We can use the TS forecast function to perform 12 steps forecasting. Okay. All right, so let's look at this activity, right? So we have uh, built the forecast model. We have built the linear regression model, right? And then now we use that model to do the forecasting for the next 12 period until December 2026, the total series. Okay. Yeah, I give you 2 minutes to perform, I think similar, right? Similar for what we just did for the SP500 linear model. Okay. This should be quite straightforward, right? And remember, we will use the same, so we will use that model, okay? We will use the model with seasonality and also the multiplicative forms. So we will use this model. We'll trend equal to 1, and the seasonal equals to true, and the type is multiplicative. Okay, but if you think you just want to use the linear trend model without the seasonality, that's fine. Okay, as long as you can generate the similar output. Okay. All right, so let's do it. Okay, for this model. Okay, for this model, let's do a forecast. Okay, for the next 12 period, because it's monthly data, right? The arrival data is the monthly data. So next 12 period will be December 2026. Okay. So your model, what is the name? Arrive22.lm. Ahead equals 12. So this will be the December 2026. Okay. And we plot. Okay. So this is the you would generate. You can see this will be the next 12 period until December 2026. So this is the forecasted value. And also you plot the forecasted value with the confidence interval. Okay. And this you plot you forecast the next 12 period. Okay. All right. So this is quite straightforward, right? Okay. Do you have any problems for activity 3.2? Any issues? So far good, right? Okay. That's great. So let's continue. Okay. Okay, so we will look at this linear regression model. Okay, we look at the linear regression model, and we mentioned, right, if your model is useful, is significant, and this will be the random terms, the random error, right? Random error, and this random error. So when we do the estimated value, this will be the estimated value. Basically, this is a mean, right, of each uh, uh, period t. Okay, so the estimated, this will be, you will have the estimated model residuals, right? So this is your actual value, this is your predicted value, right? And then this is your estimated residual. And if your model is correctly specified, this estimated residual should follow IID, which is identically independently distributed, right? And follows a normal distribution with mean 0 and a constant variance. Okay, so your estimated residual, or your residual for simplicity, right? Your residual should follows this IID normal distribution. So means all the residuals, if you plot it against uh, the estimated value, for example, y hat, right? And then that should distribute it without a clear pattern and among this horizontal line, right? This is the ideal situation. So we can look at the residual distribution, the distribution of your estimated residual to look at whether your model is correctly specified or not, right? Here we say the residual should be normally distributed. So we can use this Shapiro-Wilk test to test whether the residual follows normal distribution or not. So the null hypothesis is residual follows normal distribution. So if your p-value is bigger than 0.05, let's say 0.05, you will not reject this your null hypothesis, right? So means your residual follows normal distribution. Or sometimes you can use QQ plot, right? QQ plot, you plot the residuals along this 45-degree line, and whether the residuals are very close to this line, right? If they are very close to this line, means they are normally distributed. Okay, this is QQ plot. Assumption 2 and 3, they have zero mean and constant variance. So residual, you can plot the residual, right? For example, you can plot the residual according to the time, right? According to the time, and if the residual are this is T, right? So they have no clear, they are scattered around this T, then that means they are they have zero mean and no clear pattern. Okay, so you can use the location t-test, and the null hypothesis, the mean is equal to 0. So if your p-value is bigger than 0.05, so you will not reject H0, means the mean is 0. Okay, a mean of the residual at 0. So the last assumption is independent, right? Whether all the residuals are independent, they have no correlation. So you can use this Elgin box test, right? The null hypothesis residuals are not correlated. Remember, the null hypothesis residuals are not correlated. So you want your p-value is less than if p-value is bigger than 0.05, okay, your significant level alpha. So means you will not reject H0, means residuals are not correlated. So residuals are independent. Right? If your p-value is smaller than 0.05, so you reject H0, means residuals are correlated. Residuals are correlated, right? So means your model may not fully capture or extract the information from your time series. Okay. Of course, you look at the autocorrelation function, SAF plot, right? And if they are not correlated, means the SAF, as long as it's not like 0, means that they have no correlation, means autocorrelation should be almost 0. Okay, so this is the you need to diagnose make diagnosis of your model. Okay, so we can use TS explore function. Okay, TS explore function to see whether your model have issues or not. Okay. So let's and the TS explore function where you look at the residuals of your model. Okay, the model residuals, and we can look at the test section, and you can see location here the null hypothesis is mu equal to 0. Now you will not reject null hypothesis means their mean is 0, right? This Shapiro-Wilk test tests the normality, whether the residuals are normally distributed. Now you can see the p-value is almost 0, right? So you reject the null hypothesis, so means the residuals are not normally distributed, right? Okay, so normality assumption is not fulfilled because the p-value is almost 0. Okay, and the independent assumption, you look at this Algin box test, and the p-value is significant. So here you can say it's not fulfilled because you reject the null hypothesis. Okay, they are not independent. Okay, so means this model actually did not capture all or extract all the information from your time series. Okay, and we also actually have this stationarity test. So in seminar 4, we will look at this test, right? So this measures whether the residuals are stationary or not. And with this is the ADF test, right? The null hypothesis is there is a unit root, right, for this ADF test. Now you look at this p-value. P-value is bigger than 0.05, means you will not reject the null hypothesis. Means there is a unit root in this residuals, right? So the residuals are not stationary. Okay, so because you look at the residuals, the residual is normally distributed with mean 0. That's fine, right? It's not normally distributed, although the mean is 0. The residual is not stationary. The residuals are not independent. They are dependent. So your model actually does not capture all the information from your time series. Okay. So your model actually is not a good model. Okay. Of course, you can look at some graph, some plots from the residual, right? If you look at residual here, and we see the residuals actually they are correlated, right? And either positive, negative, and they also have a trend, right? Residuals have trend, and if you look at the variance part, the variance becomes bigger, right? And if you look at the QQ plot of the residual, and clearly they are not 0, because here you can see they are not close to this 45-degree line, and they are not close to this 45-degree line. So they clearly not normally distributed, right? The residuals are not normally distributed. The residuals have correlation, and the variance actually of residuals are not, you can say, homogeneous. Okay. So there are heterogeneous variants. Okay. And if you look at the ACF plot, you can see the ACF plot, and even with lag up to 8, right? So the autocorrelation are not different from 0, right? Are different from 0. They are clearly not 0, right? So they have a very high correlation. Okay, so means the residuals are highly correlated. Okay. All right, so let's demonstrate that. Look at the TS Explore, okay, to look at the residuals of SP500, okay, the model we just fit, okay. So this SP500 is about, right? Okay, SP500, okay, .lm, okay. So let's look at the residual. Let's do analysis on the residuals. So you use TS Explore. SP500.lm and the residuals. Okay, yeah, so this will be enough. Okay, so if you look at yeah, this is line plot of the residuals. Clearly, they have a trend, right? They have the correlated, and the variance are not homogeneous. And look at the distribution. Indeed, they are not centered distributed around, right? Although the mean is 0, but they not look like normal. If it is normally distributed, they should have quite symmetric around the mean, right? And box plot, and there are outliers. Look at the QQ plot, and they are not close to the 45-degree line. And look at the SEF plot, right? The residuals are strongly correlated. Right? If you look at the test, okay, look at the test and look at the autocorrelation, right? Up to 7 autocorrelation are not 0, okay? And if you look at the location test, right? So yes, the mean is 0, but the normality test, right? A Shapiro or Wick test, and you will reject the normality test assumption, means they are not normally distributed. And you look at the independence test, L box test, and then they are not independent. Okay, they are correlated. And if you look at of course, if you want to see the stationarity of the residuals, they are not stationary, because there is ADF, means that ADF test is not significant, means there is a unit root. Okay. Yeah, so this is you can do a diagnosis of your model by looking at the distribution of the residuals, right? And this is actually same as when you fit a simple regression model, linear regression, and then look at the residual distribution, okay? And same for the time series, okay? Because you just fit a linear regression model, and then you look at the residual, all right? So let's look at activity, right? So we look at the regression model for the arrival total column, examine whether any of the model assumptions are violated. Okay, I think it's quite trivial, right? So you just look at the uh, residual. Okay, you just look at the residual and see the distribution of the residual. So let's do it together, quite straightforward. Okay, so here this arrival total LM. Okay, okay, this is the forecast. Let's look at the residual. Okay. Okay, so sometimes you can specify the number of digits you want to keep. Digits. For example, here digits equals 6. Okay, let's look at up. Oh, a residual. Okay, residual. Okay. All right, so this is the diagnosis of your residual. You can see this is a line plot of the residual. Clearly, you can see the residuals they are correlated, right? There is a trend, and they are not normally distributed for sure, right? And if you look at the histogram, if you look at the box plot, if you look at the QQ plot, they are not normally distributed. And if you look at the autocorrelation function, they are highly correlated, right? And if you look at the test, go to the test, right? Location, and okay, mu equals 0, that's fine, right? Because the mean of the residuals is 0, and but the normality test, so you reject the null hypothesis, means it's not normally distributed. And independent test, okay, you also reject, means they are not independent, they are correlated. Of course, you look at the stationarity test, the residuals are not stationary. Okay. Look at the ACF, this PSF. Okay. So you can see this model, the fitted model, although it is significant, it extracts information, but the model actually violated the assumption, especially the assumptions regarding the random terms. Okay. Okay. Alma, you mentioned whether all assumptions need to be satisfied for the model to be valid. Sometimes in reality, okay, you don't need to satisfy all assumptions. As long as you can justify that, right? As long as your model is significant sometimes and serve the purpose, for example, it fits the data okay, that should be okay. Because if theoretically we need to ensure the residuals follows IID normal distribution, right? So mean zero and same variance, independent, identically distributed normal distribution. But in reality, this assumption actually is not easy to achieve for most cases. Okay, so if I say yes or no, no, you don't need to ensure all assumptions need to be satisfied, but you try to meet the assumptions as many as possible, and you need to justify that. Okay, and when you apply the statistical models to fit your data, all right, yeah. Okay, yeah. So let's go back. Okay, so we see we can fit a linear regression model, right, with different trend orders, or the seasonality impact, the maybe multiplicative terms, something in your model, right? So now we want to smooth the data because the data you have trend, you have seasonality, and sometimes you also have irregularity, right, in your data. So we want to smooth the data. Okay, so what we can do is we can use this simple moving average. Okay, remember this simple moving average will be different from we will discuss MA model in seminar 4. Okay, and there are different things. Okay, there are different things. Okay, they're not the moving average model. It's just the simple moving average. You want to smooth the data and use the simple moving average to do a forecast. Okay, so I think it is quite straightforward, right? For example, your simple moving average, the number of periods is equal to three, 1, 2, 3, right? For example, this is your data. YT, you have 5 data points, okay, in T of 5 periods. Now, if we use a period equal to 3 to smooth this data, so now this is your so-called forecasted or this estimated in period 4, right? Although you have this actual observation in period 4, now you want to smooth that, okay? And then in period 5, you will use period 3, period 2, period 3, period 4, and do a 3-period moving average, which will be 9, right? 4 plus 8 plus 15 divided by 3, okay? 27 divided by 3, which is 9. And the 6, in period 6, now you will use period 3, period 4, and period 5. Okay, so will be 8 plus 15 plus 7 divided by 3, which is 10. So the forecasted or the forecasted value in period 6 will be 10. Now, if in period 7, you want to forecast, okay, you want to forecast, it's still quite simple. You will use period 4, period 5, and period 6. However, you don't have actual observation in period 6. Now you will use the forecast value in period 10, in period 6, which is 10, in your simple moving average. This will be your forecast value in period 7. So this will be 15 plus, right, 15 plus 7 plus 10, okay, plus 10, then divide by 3. This will be your forecast value in period 7. Okay, this will be 22, 32, 10 and 2 divided by 3, right? Okay, so this is the simple moving average. Okay. All right, so simple moving average. Let's see what we need to cover. Okay. So the simple moving average, you can see you estimate the trend and the cyclic components, right? Because you do an average using the latest few periods observation. Okay. So it removes fluctuation in time series caused by seasonal and irregular components. So those irregular components may offset each other, right? So this in your simple moving average. You will be able to calculate the mean of a select number of consecutive observations in a time series, because this is a definition of your simple moving average, right? So for example, you want to use n period, a simple moving average. You just use the latest maybe n period observation divided by n, right? So this is a simple mean, right? The mean or arithmetic mean of your select number of consecutive observations. Okay. The average window is a time range to be averaged. It moves through the entire series. Okay, this is what we mean. Okay. Okay. This order 3 means every 3 consecutive observation will be determined and divided by 3. Right. This will be your the value. Okay. So we can use a simple moving average for forecasting, right? The idea is predict the future development of a series by aggregating the most recent observation of the series, okay? And large averaging window means more data will be introduced, including the data. Of course, the larger period in your simple moving average, then you will have more accurate, maybe in terms of the mean, right? However, the short-term volatility will be neglected because the volatility of the data will be maybe canceled off. So because you use too many, right? Too many data points to do the simple moving average. Okay. Uh, Okay, so smaller average window means n is small in your simple moving average. So it will consider the most recent data will play a big role, right? And then you will be able to capture the recent volatilities in the forecast. However, you will be losing the middle term or long term, maybe the average, right? Because you use maybe just a few recent data points to do the moving average, right? Simple moving average. All right, so how we calculate, right? Calculate is also straightforward, right? So the every moving average will be assigned to the next few period. So this is you can see we use for example the moving average simple moving average window is M, means use the latest M period observation to do the forecasting, right? For example, you stand at time T, and then you forecast T plus 1, okay? And then you use just the latest M period starting from T, YT minus 1 up to YT minus M, right? So this actually should be M plus 1, right? So you have n plus 1 data points in your numerator actually, right? This should be because t minus 0 minus 1 minus m, so it should be m plus 1 data points. Or you from yt to yt minus m minus 1. right? T minus m plus 1, okay? So this will be m data points, okay? Yeah. So there is maybe some typo here. Okay, so yeah, so for example, if you want to use moving average, the window is 3, the 3-period moving average, simple moving average. So for example, in period, you want at the beginning of the series, say t equals 2, you want to forecast t equals 3. So y is 3 hat, right? You use the latest 3 data point divided by 3. However, you don't have y0, okay? So here you don't have this forecasted value for t equal to 3, y3 hat, okay? All right, so this is, okay, so yeah, similarly, moving average, you are study at the time period t, and you want to forecast t equal to capital T plus 2. So this is the formula you are going to use. And here you don't have this yt plus 1, right? Because the time series ends at a time period capital T. So you need to estimate this, right? This will be your estimate. You will use this yt plus 1 hat. This is we just did in that simple example, right? Okay. And to forecast the future, maybe more periods, you will rely on forecast value increasingly instead of observed data, right? Because you don't have the observed data. For example, you want to forecast the y capital T plus 3, and then you will use uh, y capital T plus 4, and then you will use y capital T plus 3, capital T plus 2, y capital T plus 1. All these values are forecasted, right? You will not rely on your true or real observations. So this will not be reliable because, right, all the forecasts in future forecasts depends on your previous forecasts, okay? Okay, so we can use T as a moving average function, right? In this package to generate a moving average forecast of a time series. And this is, for example, SP500 include that time series, we use a 3-period moving average, right? The window will be 3-period. So this order equal to 3. And we want to forecast, for example, next 22 periods. Okay, so let's, and the moving average are printed in the forecast column. So this column, okay, and will be the forecasted value by the simple moving average. Yeah, and this is in your training data, right? There are no forecast for the first 3 period because you use moving average, the window is 3, okay? If you use the moving average, the window is 4 or 5, so there are no forecast for the first 4 or 5 period, okay? Of course, we can use the plot function to see your forecast. Here you can see if you plot this simple moving average, then this is the forecasted value, this in the green area, right? And with the confidence interval, okay? All right, because simple moving average, you can see this is your, the gray line is your original time series, and the red line your moving average series, and they are very close to each other, right? So simple moving average can maybe mimic or can fit the original time series very well. But if you look at the forecast, maybe the confidence interval becomes so big. And then the moving average for if you have more maybe a period to forecast, then the error or the confidence interval becomes even bigger, right? So this is what we mean here. So, okay, so let's demonstrate the simple or moving average, okay? Okay, so let's look at a simple moving average. Let's create a simple moving average model, use SP500 and close data, okay? So we say SP500 close simple moving average with period 3. The window for the moving average is the number of windows is 3. We use TS moving average, okay, and SP500 close, and the order equals 3 means the window used in a simple moving average is 3. Okay. Let's mute the plot. Okay. And let's look at the forecasted value in the next 24 period. Okay. 24 period. Okay. You can uh, print it out. Okay. So this is a forecast, right? Forecasted, column, and we don't have for the forecast for the first 3 period because we use order 3, and then you go ahead, you look at the forecast for the next 24 period, okay, for the next 24 period. Here you can see here is the forecasted column, right? Forecasted column with confidence interval. Okay. Error and a confidence interval. Okay. Yeah. So you want to plot. You look at the plot. Simple moving average with period 3. So this is you can see your original time series is a gray line, and your moving average is a red line. They very close. They are very close to each other, and this blue area is the forecasted value. Okay, so you can see the confidence interval becomes bigger, means the error becomes bigger. Okay. All right, it's quite straightforward, right? As long as you can follow the examples, you should be able to generate the same result. So let's do this activity, okay? Then we will have a 5 minutes break, okay? So let's calculate the simple moving average of the total series, and with order 6, 12, and 24. Okay, so the window, right? The window in the moving average. Until then we do a forecast, which is 12, right? 12 period. Okay. Okay, 12 period, because this is a monthly data. And okay, compare the forecasted value of the past and future between the 3 simple moving average orders. Okay, so I give you 5 minutes because you need to create 3 simple moving average model with the order 6, 12, and 24. Okay, and then you can do a comparison and look at their forecasted value. Okay, 5 minutes, right? You just follow what we for the examples shown on the slides. So use TS move moving average function. Okay, create three simple moving average model with period 6, 12, and 24. And then look at the output or look at the forecasted value for the next two period, the next 12 period. Okay. All right, so let's do it together, right? So we create three simple moving average for the total arrival total series, okay? So the first one, we arrival, maybe I arrival total 6 simple moving average with period 6, TS small, okay? Arrivals total series and order equals 6. And let's maybe also plot the original value and the moving average value. Okay. So the next 12 period, which is until December 2026. Okay. Let's look at arrival to 6. Okay. So if you want to print just the forecasted uh, value or maybe a few, so let's use this tail equals to 20. Let's see what we have. Okay. So we will only plot the last 20 rows. Okay. So here the forecasted value for the next 12 period. Okay. And this is the standard error, the confidence interval, right? Okay. So you can then you can create the period with 12, order 12. TS moving average, arrivals total, order equals 12. And you want to show the plot. And you want to forecast in the next 12 period. Okay. Want to print it out. 12. Okay, so you can make a comparison. Okay. And if you look at the red line and the gray line, okay, so for all the 12, all the 6, so maybe there are maybe some spikes, right? A higher spike. And similar, right here, this order 12 with a moving average window, which is 12. And compared to this 6, moving average window equal to 6. So it becomes more smoother, right? Smoother. And if you look at the red line for order equal to 6, so there are some not smooth for the red line. Okay, so then if you let's look at even maybe the arrival total at 24. Okay, order equals 24. Okay, okay. Okay, so let's look at even you will see the if you look at the red curve, red line, so the red line becomes even more smoother, right? Smoother. Okay, so means the more period in your simple moving average, right? The more smooth the data you will get. Okay. All right, so this is activity 3.4. Okay, so it's quite simple, right? So I will not stop here. So I believe you should be able to follow, right? You should be able to follow all the codes, and because the codes also available, right? So let's do a simple discussion. Okay, then we will have a 5 minute break. So discuss the following statement. Simple moving average can estimate the trend and the cycle components of a time series. We just say yes, right? Simple moving average, right? Because you can estimate the trend, right? Whether it is increasing, decreasing, and by using maybe the latest the N period data and taking average, you will see the trend. And also the cyclic components, right? Because if there is cycles and your simple moving average data, the series also have cycles. Okay. So it removes fluctuation in a time series caused by the seasonal and irregular components. We say indeed, right? Because when you do simple moving average, maybe those seasonal impact and irregular component will be cancelled out, right? The more period you use in your simple moving average, and then the more smooth of your simple moving average series. Okay, so it will be able to remove your seasonal and irregular components indeed. Okay, now the second one, if the simple moving average were not used for forecasting, okay, we will not use simple moving average forecasting, but simply to estimate the trend and the cycle components. So what would you assign the estimated value instead of the one period after the moving the average window? Okay, so what does this mean? So suppose this you have maybe let's say 3. Okay, the average window is 3 period to do the simple moving average. Okay, now you stand at the time point t. Now you are asked to forecast, for example, in t plus 1, right? T plus 1. So what are you going to assign a value for this forecast? Any idea? Suppose, okay, suppose maybe this yeah, the time series is up to time point this period t. Now you want to forecast this yt plus 1, and you will not use this simple moving average to do this forecast. So what values you are going to assign, or what values you think it is appropriate for this forecast? Any idea? Can you follow my question? Can you follow my question? So suppose you are not using the simple moving average to do the forecast. Okay, so what values you think it is more appropriate to put it here? So you want to forecast the value in period t plus 1, and your data is only up to time period t. You want to forecast the value in t plus 1. Any response? Okay, Nicholas, the last three values average is the same as actually your simple moving average value, right? So we just did a simple example. So now you are not assign that average value of the last three observation as your forecast. So what values you will consider? Maybe this question is not quite clear. So basically, so what does this mean? So this in period t and previous t minus 1 and previous t minus 2. Maybe you also have maybe a t minus 3, so on and so forth. Okay. Yeah. So when we say moving average, right? So we get the maybe for example, you use Windows 3, right? 3 windows to do the simple moving average. So and there's maybe t plus 1, right? So when we do this, we actually use maybe from t minus 1, t minus 2, right? These three values, the average of these three values, right? As a forecast for t plus 1. This is what we mean by this simple moving average, simple moving average. So what does this question mean? This question means, for example, let's say t impurity. Okay, let's say impurity. Impurity, when you do the forecast, you use t minus 1, t minus 2, t minus 3, the three moving average here, right? Three period average as the forecasted value in period t. So what you are going to do is, if you are not assigned that value, and what you are going to do is, okay, so we are going to, for example, in period t, we use the average of the, you can say we can use the average of the past three period. Okay, so another you can consider, for example, we use three period, for example, y t minus 1 plus yt plus y minus t plus 1. So what does this mean? So if we use this value to replace the usual simple moving average, which is from yt minus 2, let's look at period t, okay? So we use y2 plus yt minus 1. Actually, this is t minus 3, right? T minus 3, t minus 2, and t minus 1. So this is what we mean by here, simple moving average, right? So we use the latest three period to replace, to forecast the value at period t, okay, at period t. Now what we are going to do is we can use this way, right? Yt minus 1 plus yt plus yt plus 1 divided by 3, and then we put it at time t. So this actually means you do a centered moving average, right? This is actually my understanding of this question mean, okay? So this means besides the simple moving average, what we can do is we can use the so-called the centered moving average. We take the center of the period, for example, t, as the center. Then up to previous few period and the next few period, and then the average. This is called a centered moving average. We can use that value to replace your simple moving average value. If you already remove the, for example, you estimated the trend and the cycles. This is what does the question mean. All right. Okay. So there is another moving average called a centered moving average. Okay. The formula will be different from what we learned here, simple moving average. The simple moving average, we use the latest n period data observation, right, to do the forecast or to do the estimate. Now the centered moving average means for the period t, we use the t as the center, and then next the previous a few period and next a few period, then take the average. So this is a centered moving average. Okay. Okay. So yeah. So basically, moving average, you can see remove the trend. Okay, so the Grace have a question. Okay, how do we decide the order number to use? It's a good question. It's a good question. So it depends. For example, if you look at your original data, and if you want to smooth the cycles, you look at what is the length of your cycle. For example, if your cycle is 1 year, so you can maybe use the year, for example, if it is monthly data, and usually maybe the seasonal, there are 12 seasons, and the cycles maybe the length is 1 year something, so you can use 12. Okay. It is a line that best fits the actual, the gray line. The gray line, you mean the plot from our model, right? The gray line refers to the original time series. As we increase the order number, the red line gets, yes, you have more period in your window. So the moving average series will become more smoother. Because smoother, but it moves away from the gray. That's correct. Because the more period you use, you will calculate, you will be able to get the mean, right? For example, if you use all the data points, the extreme case means you use the mean, right? The mean to replace everyone. But theoretically, yes, yeah. So the more period you use in your simple moving average, the smoother of your forecasted values. And so how many period you want to use depends on your purpose, right? If your purpose is to smooth the time series, you want to remove the cycle impact, you want to remove the seasonal impact, you want to remove maybe the irregularity components. So the more period you use in your simple moving average. Okay. However, we say there is a trade-off, right? So the more period you use, and the smoother of your forecasted values, and but you will not be able to capture the recent volatility of your or maybe of your data, especially if your data, your time series have a higher volatility, and then you may consider, in order to fit the data more closely, you use a smaller number of period in your simple moving average. However, so this is why I say it depends on your purpose, right? If we want to have a more smooth time series, right, remove all those components, the cycles, the seasons, the irregularity, you use a higher number of periods, right, in your simple moving average. Okay, it's a good question, because I think in seminar 1, I mentioned sometimes fitting a statistical model is an art. Okay, it depends on it's not, there are no so 100%, for example, a correct thing like mathematics, right? So statistics are sometimes is art. Okay, yeah. Okay, great. Yeah. So let's have a 5 minutes break. All right. So then we will do a exponential smoothing. Okay. All right, we are back. And Grace, actually, your question is very good. Yeah. Besides, for example, you need to be clear about your purpose. You also can do, for example, model evaluation. For example, which model fits the data where, right? So determine the number of periods you want to use in your simple moving average model, right? So we need to do evaluation, model evaluation at the end of today's seminar, okay? So let's continue, okay? So exponential smoothing, okay. Exponential smoothing, okay. So this should be easy to understand, right? So here, basically what you are going to do is, for example, your assume, okay. For example, your we say alpha equal to 0.3, and later we will know what do we mean by alpha, okay. So we multiply the most recent values of, for example, this your expense, right, in February, and this is your expect predicted. Suppose your predicted in February is 3840, okay, and then you are going to predict the value in March 2024. So what are you going to do is you take the weighted average from your actual expense and your predicted expense. The alpha you 0 point equals to 0.3, okay, and then this will be your predicted value for March 2024. Okay, here is so-called the exponential smoothing. So okay, so this is the formula. Yt hat equals alpha yt plus 1 minus alpha yt minus 1 hat. Okay, so this is so originally you see exponential smoothing is to smooth a time series by taking the weighted mean of the current observation yt and the most previous forecasted value yt minus 1 hat, right? So we get this smooth theory, right, to smooth your original time series. Okay, so this is what we mean here. Now, if this is alpha refers to this smooth parameter, alpha should be in 0 and 1. Okay, and so if so the purpose, you can see we use your observation and use the previous period forecasted observation, the weighted average or weighted mean, to get the so-called smoothed or forecasted predicted value of your original series. So this is the purpose of smoothing. Okay. Okay, now in terms of forecasting, we can use the exponential smoothing to do the forecasting. So this is what we mean here. So this is a weighted average. For example, you want to forecast the value in t plus 1, in period t plus 1, right? So this will be the weighted average of your period t observation plus period t forecasted value. And then you assign this value to the forecasted value in period t plus 1. Okay, and because you can see yt hat equals, if we use this formula, then you can see yt hat equal to the actual value, the weighted average of actual value in period t minus 1 and the forecasted value of predicted value in t minus 1. And you do this until you come to the second period, right? Second period, you can see the forecasted value in second period equals the weighted average of your first period plus the forecasted value in period 1. Okay, and this value actually depends on y0 and forecasted value in period 0, right? So which does not exist. Okay, and so we need to set a value for y1 hat. Okay, this is what we are going to do. Do in if we apply the simple exponential smoothing in forecasting. Okay. So you can see the original purpose is actually to smooth the time series. Now we can apply the simple exponential smoothing to do the forecasting. Okay, there are some, you can see some of the formula are different. Okay, when you want to smooth, your time series, and you can see these are the weighted average of yt plus the forecast value for weighted this yt minus 1 hat. But if we apply this simple exponential smoothing in forecasting, what we are going to do is the forecasted value in t plus 1 equals to the weighted average of t, period t observation, and the forecasted value in period t. Okay. All right, so this is a simple moving average. Now, if use a simple example, you can see if you want to forecast 2 period ahead. Okay, so this is a formula you will apply, and then this yt plus 1 hat, right, will equal to this guy, right, will equal to alpha times your yt plus your 1 minus alpha yt hat, right? Okay, so because this yt plus 1 hat does not exist, yt itself does not exist. So what we are going to do is, so you don't have this value, how can you forecast t plus 2? So you will use your forecasted value in period 1 t plus 1 and substitute into this formula. Then you will see your 2-period forecast will exactly the same as your 1-period forecast, right? Because you don't have this yt plus 1 value, okay? So you will use your forecast value. So what we mean here is, as a result, the future forecast remains a constant regardless of number of forecasting period, always equal to this y plus 1 forecast, t plus 1 forecast. And this will equal to alpha yt you have, right? Alpha yt you have because yt already observed, and 1 plus alpha yt forecast, okay? And yt hat equal to this alpha yt minus 1 plus 1 minus alpha times yt minus 1 hat, okay? So you can see this is a simple exponential smoothing when applied in forecasting. So we will have a constant forecasted value for any period which is greater than 1, right? So it's only suitable for series with no trend and no seasonality, right? Because all the future forecasts will equal to this guy, this yt minus 1. Yt plus 1 hat. Okay. Forecasting. Okay. These are forecasting. Let's look at it there. Simple. I think this example should be quite easy to understand, right? Suppose alpha equal to 0.3, and for July. Okay, July. For forecasted value by simple exponential smoothing for July will be this guy 0.3 times this guy plus 0.7 times your forecasted in period June 2024. Okay, so it will be 3988.3. And then you will assign this forecasted value when you forecast maybe 2 period ahead. You will assign your forecasted value in your previous period as you have observed that, and eventually you can see all the forecasted beyond 2024 July, they are exactly the same number, same forecasted number. Okay, so this is what we mean here. All right, so we can use this function TS exponential ESM, exponential smoothing function to forecast, okay? And then order, we will set it as simple, okay? Because later we will have uh, uh, double exponential smoothing. We also have hotter winters model, okay? So we will set order equal to simple, and this alpha, that parameter equal to 0.3 something, okay? And if you do not specify this, and R will estimate the best fitting value. So for example, to minimize the sum of squared errors. Right? So this R will estimate a best alpha for you. Okay. And then we can use a TS forecast function, yeah, based on this model, simple exponential smoothing. And we can, for example, show the plot. And this plot is a forecast value, okay? So let's do it, okay? Let's demonstrate it quickly. This is what we have. Oh no, SP500, okay. SP500. I mean, yeah, here. So SP500, we use a simple exponential smoothing equals TS exponential smoothing SP500 close. Order, okay, order equals to simple, okay. This means we use a simple exponential smoothing, alpha equals to 0.3, okay. And if you don't specify alpha, so R will estimate the best value for you. Remember, alpha must be in 0 and 1, okay. SP500, simple exponential smoothing. Okay, let's see. Okay, so this is SP500. You can see alpha. You set you set the value equal to 0.3, and some error measures. Later we will discuss the model evaluation and also the some information criteria. For example, log likelihood, AIC, ISC corrected, and BIC. Okay, criteria. And okay, so let's do a forecast. Let's do a forecast. For example, SP500, simple exponential smoothing forecast. So let's use the TS forecast function. And this is your model SP500, simple exponential smoothing. You want to forecast, for example, 6 period and shoot the plot. Maybe let's say equals true, so you will see the forecasted the plot. Okay, forecast then include equals, we just see the plot the forecasted value. Okay, and let's see the forecasted value. Yeah, so let's see what we have. Here you can see this is a 6-period forecast using a simple or moving simple exponential smoothing. Okay, with alpha equal to 0.3. Okay, alpha equal to 0.3, and you can see the plot. Okay, now you can see all the forecasted values actually the same thing, the constant. Okay, the constant. However, the error becomes bigger. Okay, so this is a simple exponential smoothing. Okay. So let's look at the results in slide 18. And 19 conclude on the problem of simple exponential smoothing model. So basically, whether alpha equal to 0.3 is good or not, right? If we look at slides 18 and 19, okay, 18 and 19, especially for the 18, if you look at the residual, right? If you look at residual, actually, the residuals are not IID normal distributed, right? And also the residuals are correlated, okay? So what we are going to do is you can specify, you can ask R to get the best, best alpha, okay? Best alpha. So you don't need to specify here. Let's go to this. You will not specify alpha equal to 0.3, right? If alpha equal to 0.3, there could be still strong correlations uh, between the residuals. Okay, so we can specify uh, okay, ST500 uh, exponential smoothing. I want to use the consistent, okay, simple exponential smoothing. Maybe best alpha, okay. I use uh, so let so you can see if you look at that correlation of your residuals, they are much correlated, right? The correlation is very high, almost equal to 1 ACF, okay, with lag. You can see uh, if you ask this R to estimate the best alpha for you, alpha almost equal to 1. Actually, it's not equal to 1, but let's look at maybe, for example, number of digits equal to 6. So it is 0.0099 something, okay? So it's almost equal to 1, right? So here, if you use alpha equal to 3, might not be the best model, okay? Your simple exponential smoothing may not be the best model, all right? Okay, so let's, what is the activity, right? Calculate simple exponential smoothing on the total, right? With let R estimate the best alpha for you, or calculate the forecast for the period until December 2026. So let's do it together. Let's just do this ST500, right? Okay. Oh, this is arrival total. Then a simple moving average, simple small exponential smoothing. Let's say uh, arrivals total and all the equals to simple. Okay, and let's look at the model. Okay, let's say 6 digits. Okay, so this is the model and the best alpha is 0.25. Okay, and so let's forecast the next 12 period. Okay, your model simple exponential smoothing forecast. Next 12 period and forecast. That's only include plot the only forecast value. All right, so this is what you will get. So the forecast for the next 12 period. Okay, yeah. Yeah, we mean, right? We mean, yeah, you can see we ask R, okay, we ask R to estimate the best alpha for you, okay. And sometimes, of course, it depends on which alpha. It also depends on your purpose. Okay. So, for example, you want to say, I only want maybe 50% of the impact from the latest observation. So you can say alpha equal to 0.5. Okay. Yeah, so this best alpha maybe depends because are estimated based on the minimum total squared variance something, okay? Or you use best criteria, the criteria to select which alpha is the best. So, but it may lack some economic or managerial implications, right? Because it's just statistically this is the best alpha, right? So it also depends on, for example, some the specific economic and managerial scenarios when you select the alpha. Okay. All right. So let's go back. Yeah. Let's go back. Okay. So double exponential smoothing. Okay. Double exponential smoothing. Here, the simple exponential smoothing. We look at if you look at that the model, you can see we do not capture the trend, right? So especially if your data, your time series has a trend, and your simple exponential smoothing will not be able to capture that trend. So what we are going to do is we will introduce another exponential smoothing term, which is a trend. Okay. So here, this LT and LT minus 1 refer to the level. Basically, this is the estimated value in your trend line. Okay, and this is the difference of these two levels will be the you can say the slope, right? This we define this as the slope. Okay, and then so we want to not only estimate this level but also estimate this slope. Okay, so this is what we are going to do. Okay, so this should be let the BT actually, right? From t minus 1 to t. BT is the estimated slope of between these two periods, and hence this LT minus LT minus 1 equal to this slope. Okay. So this is the model, the double exponential smoothing. You can see there are two smoothing functions. Okay, one is the level. Okay, the trend levels. So this is your observation YT and alpha and 1 minus alpha. This level plus this trend. This actually there's a level plus a trend your estimate in your trend line, right? And then this slope will be another weighted average. Okay, beta times LT minus LT minus 1. This is uh, your slope, and then estimated slope LT minus LT minus 1, right? Estimated slope in time t, and then your slope in t minus 1, right? BT minus 1. You can see there are two parameters, alpha and beta. Okay, alpha refers to the exponential smoothing on the level, while beta refers to the exponential smoothing parameter on the slope. Okay, and then your estimate. Okay, your estimate. For example, you are standing at time t, so h period ahead, yt plus h, yt plus h hat will be the level at time t plus uh, h times bt times this period. Okay, so this is estimated value at t plus h period. Okay. All right, so this is so-called double exponential smoothing. You don't need to remember this this formula, but you need to know what does alpha mean, what does beta mean. Okay, I honestly I cannot remember this formula. Okay, we have too many formulas. Okay, so this I think we have this simple example, right? So I will not go through this. This should be you can, for example, in the initial value in February 2024 is 3610. And we simply take this value as the level in this period. And then the slope will be, the initial slope is the difference between the series and uh, your previous series, right? The difference of the two series will be your slope, which is 230. And then your forecasted value will be this the level plus the slope, right? This is 3380. And now the level, we use alpha equal to 0.3. And the level in March is uh, this your actual value in March plus your forecasted value in this is in previous, right? This one, okay? And then 0.7, this will be this level. You estimated level, okay? This is 3536, okay? And then you will get the slope. The slope, you estimate the slope, suppose you use beta equal to 0.5, 0.5, and then this you go back to the formula, okay? This will be a level difference of the levels, the two levels, and times the beta plus 1 minus beta, which is 0.5, times the slope you estimate in period, which is negative 230, which is a negative 152. Okay, so this is the step. And then the forecast value will be your level, right? The level plus your level in t plus 1 period times the times this slope. This is negative 1 times 1 negative 152, which is 3384. Okay, so this is the forecast value. Then you can do this following all this the double exponential smoothing or hot, very hot exponential smoothing model, and then you do the forecast. Okay. So we can use a TS exponential smoothing function. However, when you specify the order, right, the order is not simple, right? Now it's hot, means double exponential smoothing. So hot method. And you have two parameters, alpha and beta. Okay, alpha and beta. And if you don't specify these two, so R will estimate the best alpha and beta for you. Okay, maybe based on the minimization of the total variance, squared errors, and all the minimum information criteria. Okay. Okay. Then you can use the TS forecast and same thing. Okay. So let's do it. Let's look at the discussed question. So whether the hot exponential smoothing with alpha equal to 0.3 and beta equal to 0.05 is appropriate or not. Basically, you can ask R, okay, to get your best alpha and beta for you, okay. So we will demonstrate, maybe first demonstrate the examples in the slide. Okay. The double exponential smoothing, we use SP500 data, okay. Yeah, here. So we will create SP500 hot model, okay, TS exponential smoothing SP500 close and order equals to hot, okay, and here alpha equal to 0.3, beta equals to 0.05, okay. We look at the model, okay, SP500 hot, okay. So this is the model. You will see some of the information, for example, the error measures, the information criteria, okay. And let's do 6-period forecast. TS forecast, okay. Your SP500 hot and 6-period, okay. Let's look at the plot. Okay. Let's look at the print out the forecast. Okay. Okay, so this is a 6-period forecast, and this is the plot. So quite straightforward. But if you want to ask, maybe for example, ask R to estimate the best alpha and beta, the two parameters for you. Let's look at what are the values. So here you can see alpha equal to 1 and beta equal to 0. So actually you can see, or if you want to see, for example, maybe 4 digits. So you can see alpha equal to 0.999 and beta equal to 0.001. Okay, so this is the best alpha beta estimated by R. Okay, yeah. So let's move forward. So basically you can see you use alpha equal to 0.3, 0.05 may not be the best parameters, right, to fit your original time series. Okay. So total, I think this we will skip this, okay? So this is quite straightforward. You can just follow what we did in the slides, okay? You use a TS exponential and specify order equal to hot and alpha and beta. You can ask R to estimate it for you, okay? Maybe simply we do it quickly. It's arrival total hot. Yes. Smoothing. Arrivals total, right? Order equals hot. Okay, yeah. So this will be the best value. And best value. And you can do a forecast on for the next 12 period. We will see. Okay, yeah. So this is your output. Okay. All right, so this is a hot method, means double exponential smoothing. Okay, so we go forward to see the hot wind. Now we want to capture the seasonality. Okay, not only the trend but also seasonality. Now this is the hot winters method. So there are three parameters: alpha, beta, and gamma. Okay, so this we will have additional equation to get the estimate of this seasonal impact. Okay. However, when you do this, you can see we need to subtract the when you, in your level estimate the smoothing function, you need to subtract the seasonal impact, right? And the same for the slope. And this is a seasonal or exponential smoothing. Okay, so I will not to go through these details. You can read the slides. And when you estimate, for example, each period ahead of forecast, then this is the level in period t plus the slope times this in t and times the time period h and plus the seasonal effect from the most recent season. Okay, for example, this is example, right? This April, T is this April, and you want to forecast T plus H equals June next year. So the seasonal will be the June this year, right? Okay. Do we always apply smoothing whenever we want to do for? No, this smoothing means this is another way. So let in seminar 4, we will use another way. For example, difference, right? To remove the trend or remove some of the cycle, something. Okay. So here with now you are dealing with your time series, and the time series has trend, has a cycle, has seasonality. Now you want to smooth that the time series, and also you want to apply this method to forecast, right? So you can estimate a linear regression model. You can use simple exponential smoothing. You can use moving average. You can use this hot method. You can use this hot windows method. Okay, so yeah, you don't need you should don't need to always apply smoothing, right? Whenever you to do forecasting, right? If all tests pass, yes. So basically, when you get a time series, so first we need to look at whether they have trend seasonality cycles, and then of course we need to use, for example, this method to remove those trend, remove cycles and remove seasonality, and then we test whether the time series is stationary or not. And if it's not stationary, so we continue with, for example, difference method or the other method, right? To make the time series stationary, a stationary time series. And then we apply, for example, letter AR model, MA model, AMA model, right? To extract the information. And then we test the final residuals, as you said. We test the final residuals. If the residuals follows IID normal distribution, that's great. So our model captures all the necessary information, right? So done. Job, your task is done, right? So you look at your residual. If your residual follows a normal distribution, IID normal distribution, right? And constant variance, no correlation, like we say white noise in seminar one, I mentioned, right? If your residuals are white noise, that means you have extracted all the necessary information from your time series and you don't need to do further. So your job, your analysis will stop. Yeah, until your residuals are white noise. Yeah. Okay. Yeah. All right. So we have hot winters method. Okay. Hot winters method. Yeah, so this is I think this is the illustration of this method, okay? Uh, it's not working here. Yeah, so this is the illustration of the hot winters method. Let me share it again. Yeah, so let's look at it as a quick example. So it's quite complicated, okay? So basically, because there are three components, right? The level, the slope, and the seasonality. So, and with three parameters. Here, we use alpha equals to 0.3, beta equal to 0.3, and also gamma equal to 0.3, okay, to illustrate the workings of hot winters method, okay? So basically, you don't need to remember, okay? You need to remember the formula, okay? Because I cannot remember, okay? So this complicated hot winters method formula, three formulas, okay? And so let's look at how we can use R, okay. Here in R, same thing, we use TS exponential smoothing. Here order, you need to specify hot and winters, okay. Hot and winters, and you give the parameters. If you didn't specify alpha, beta, gamma, the three parameters, I will estimate it for you, take the best estimate, okay. And all right, so we can use the forecast, okay? Similar, we can use the forecast. For example, we forecast the 6 period ahead, and then you can see here, compared to the hotter, hotter method, means double exponential smoothing, you see this seasonality. Okay, in the Hottest method alone, you just see a trend line, right? Because you only estimate the trend. Now the hot winters method also help you to get the seasonality. Okay. All right. Of course. Let's do it. Okay. Let's go to the SP 500. Okay. SP 500. This is SP hot best, right? Okay. SP 500 hot winters method. You use TS exponential smoothing SP 500 the data, and order equals to uh, hot winters. Okay, and alpha, we say alpha equal to 0. Uh, hot winters method. Okay. So now let's see whether we can get this alpha equals to 0.3, beta equals to 0.05, gamma equals 0.01. Okay, let's see whether we can have the model at P500 and W. Okay, it equals, let's say, okay, so you can see we cannot get the hot winters model. Okay, why? Because in the hot winters model, we need to specify the seasons. Okay, the period of season. Okay, so what we are going to do is we need to specify the number of seasons in your data. Okay, what we are going to do is we need to specify, okay, the SP500 data, okay, and you need to let the R know, so how many period in your data, okay. So here this is a frequency parameter. Here, let's say there are 4 seasons, okay, 4 seasons. 4 seasons, okay. So here we need to specify the seasons in the data. So we suppose we assume there are 4 seasons, okay. Then we rerun this. Now you can see we can get the hot winters method, right? We use a model, hot winters method, alpha is 0.3, beta, gamma, and then there are some of the model or information, fitting information, the information and the errors, okay? So let's do a forecast, right? Plot the forecasted value, okay? Let's print the forecasted value. Okay, so this is, you can see the forecast will take into account both the trend and also the seasonality. So there are maybe peaks or troughs of this in your forecast, not like the winter semester alone. All right. So here you can see you need to let R know that the period of the number of seasons in your time series, so that you can apply the hot winters method. Okay, without that, you might get an error message. Okay, and if R can identify, for example, the period, if it is monthly data, and maybe the R can identify that the seasons will be equal to 12. Okay, otherwise you need to specify that. Okay. Okay, I think we almost run out of time. Okay, so here you can ask R, right, to get the estimate of this alpha, beta, gamma for you if you did not specify that in your model. Okay, yeah. So the last point is about a model evaluation. Okay, model evaluation basically here we mentioned earlier you will we have many criteria. For example, the mean, absolute, percentage error. We use mean absolute deviation, mean squared deviation, and the information criteria. This is the RKK information criteria AIC, and so this will so the lowest value of this criteria, the better of the model, right? So you want this model, all this the smallest, right? So when you compare which model is better, right, you may specify different models with different parameters. For example, here you use this simple exponential smoothing. You specify alpha equal to 0.3, and you look at these criteria. Okay, these AIC criteria, AIC corrected, this is referred to AIC corrected criteria, means you consider the sample size, okay? And this BIC refers to Bayesian information criteria, right? All this may help you to select which model is better, okay? For example, you consider a few alpha equal to 0.3, maybe alpha equal to 0.1 something, right? Which model is best fit. All right, so we use this TS model evaluate function, TS model EVAL, evaluate function to obtain this information criteria. Of course, you can use other, for example, you use TX Explore, right, to see your original data, and sometimes also that will display some of the criteria. Okay. Okay, so I think we don't have time. Yeah, we have a lot of things to cover today. And yeah, you can follow the examples, okay, examples in the slides to do the model evaluation. For example, let's evaluate the simple exponential smoothing we created, okay? Simple exponential smoothing. Here, I put it here. So you evaluate, okay? So a simple exponential smoothing evaluation. We use the TS model evaluate this function, and SP500 we created it earlier with alpha equal to 0.3. Okay. Let's see SP500 simple exponential smoothing. Okay. You can see you have all these criteria. You can see these errors, indicators, and others, right? All right. So yeah. So this is all for today. I'm sorry we have 2 minutes delay, and we will continue with a lot of things in seminar 4. Okay. Seminar 4 also have we have a heavy task to do. Yeah, and let me know if you have any questions. Okay, any questions. And after today's seminar, okay, you should be able to work on your GBA. And some of you, yeah, when you work on with your team members, do work with each other closely. Okay, we don't want the situation to happen where some members like complain other team members. Okay, yeah. All right, this is all for today, and let me know if you have any questions. You can leave the meeting now. Enjoy your evening. Yeah, I see you in seminar 4. What count? Okay. Su Pia, right? Su Pia Pile. Let me see. I don't think there is a word count, right? No word count. Okay. No word count. Yeah. Okay, great. All right. For the rest of the first students, I'm going to terminate today's meeting and enjoy your evening.